Hello there guys, welcome back to another epic and execrable maths video. In this video we have another improper integral. In this case it's the integral from 0 to pi of tan x. Now this maybe looks like a slightly innocent integral, right? It doesn't really look that bad as long as you know how to integrate tan x. It's not really a big deal. It's like, okay, it's fine. But actually it's going to be slightly more dubious than maybe we think. Okay. So what I've drawn over here is the graph of tan x for a start. And I've also shaded in the kind of area that we're trying to find by doing this integral. So it's the region bounded between the function itself and the x-axis. So between 0 and pi, the shaded or like lined, whatever, like pseudo-shaded region is given right there. Now, at a glance, it might look like the answer to this should just be 0, because even if we have a divergent integral from 0 to pi over 2, if this is infinity, then surely this down here should just be minus infinity, and they should just cancel out, and we just get 0. But actually that's not how it works. In this video, I'm not going to go through an explanation as to why that doesn't work, but I'm just telling you, you can't cancel these out if they're both divergent. If they're both convergent, then you absolutely can. If this area was equal to like 100 and this was minus 100, then there's no issue. But if this is infinity and this is minus infinity, even if they're the same infinity, you cannot cancel them out. So that's why this is quite a hard question, because you need to know that. So let's just go through the working out and see what we can do. And I'm going to talk you guys through exactly how to deal with this. So the problem, the improperness of this integral is not coming from 0 or pi. It's coming from the fact that there is an asymptote in the middle of the region that we're integrating over. So if there is an asymptote or a discontinuity or anything like that inside of the integral, inside of the region I mean, then it's also an improper integral, and we need to be very careful, okay? There is an asymptote in the middle, so we need to treat this like an improper integral. How do we do that? We haven't seen a question like this before. Well, we do have to split it, just like in the last video on improper, playlist in the description, link to the previous video in the description. We have to split this into two integrals. So it's the integral from 0 to pi over 2 of tan x plus the integral from pi over 2 to pi of tan x. Okay, and if this is convergent, both of these have to be finite. If one or both of them is infinity, it's a divergent integral. Even if, as I said a moment ago, even if this is like some sort of infinity and this is just the exact negative, they don't cancel. But as I say, I'm going to explain this. So of course, as always, we should be taking the limit. So we should write this as the limit as t goes to, in this case, pi over 2 of the integral from 0 to t of tan x plus the limit, and yes, we do have to do the limits separately, as t approaches still pi over 2, but this is from t to pi of tan x. Okay. Right, now tan, maybe you don't know, maybe you do, tan integrates to the natural log of sec x, okay? So, and there's also absolute value signs around that. So let me write this down here for you. Limit as t approaches pi over 2. So tan integrates to the natural log of the absolute value of sec x. That's a standard integral, but to be fair, not many people remember it, so no worries. Normally you have a formula book or something anyway for this kind of thing. And then we have the limit again as t approaches pi over 2 of the same thing, the natural log of sec x. Like that, from t to pi. Cool. Okay, now let's start plugging some stuff in. So this is the limit as t approaches pi over 2 of the natural log of sec t, and I guess I should still have the absolute value signs there just in case, minus the natural log of sec of 0. Okay, that's the first one. And then this one, we have the limit as t approaches pi over 2 of the natural log of sec of pi minus the natural log of sec of t. The natural log of sec of t. Okay, it's a bit long-winded, of course. Now, you may be thinking that we could do some sort of combining or something like that, but actually we can't, okay? So do you see how in this integral, we have the natural log of sec t, and over here we have minus the natural log of sec t. If we had written this as one big integral, or if we hadn't, maybe in other words, if I'd written just the limit as t approaches pi over 2 on the very outside, you might be tempted to try and cancel these out. What I'm telling you, and again, I'm not going to explain it in too much detail because it's very complicated, but what I'm telling you now is this and this don't cancel out, even though they're both approaching pi over 2, or the natural log of sec of t as t approaches pi over 2. Same thing over there. It looks like you should be able to cancel them out, but actually you cannot. This has to be evaluated. This has to be evaluated. They have to both be finite, and then they can cancel out. But if one of them is infinity, or if they're both infinity, game over. Can't do it. So let's actually evaluate this. So what is sec of pi over 2? Okay. Well, sec, let's write this over here. So sec is obviously 1 over cos. So sec of t is 1 over cos of t. And cos of pi over 2 is 0. So we have 1 over 0, infinity. That's not good. So this is equal to infinity minus, and then we don't even necessarily really care about this too much. Sec of 0 is 1 over cos of 0, but cos of 0 is 1. So it's just 1 over 1, which is 1, and then the natural log of 1 is 0. So that's just like 0. And then over here, what is sec of pi? Well, this is, let's do that here. Sec of pi is 1 over cos pi, which is 1 over minus 1. So minus 1. But then we're taking absolute value, so it becomes the natural log of positive 1, and that's just 0. And then finally, this is like minus infinity. So we basically have infinity minus 0 plus 0 minus infinity. And I just want to emphasize, these infinities are kind of like the same, right? Because it's the same function. It's not just any old infinity. It's the exact same function. And all we're doing is trying to take one away from the other. But we can't. You cannot cancel this and this out. I have to emphasize it. You cannot cancel it out because one of them is divergent. The whole thing is divergent, okay? So this is divergent. Now you might say, okay, it's divergent, but what's it equal to? Is it equal to infinity or is it equal to minus infinity? Well, this is a different type of divergence. It doesn't necessarily mean that the area is infinity or minus infinity. And on an intuitive level, the area is 0, or like I should say the signed area is 0. If this is positive area and this is negative, then on an intuitive level, yes, it is 0. It's just that this area is actually just infinite, and this area is also just infinite but negative. And so it's just mathematically not okay to cancel them out. So it's divergent. I would say on an intuitive level, yes, the total thing is just 0, but mathematically we can't actually say that, and we have to say that it's divergent. It doesn't necessarily mean that it's equal to, it has an infinite, a positive or negative infinite area, it just means that it's a divergent integral, because that's kind of how we define them to be. Okay, so hopefully that makes sense, guys. It's a difficult one to explain and like really get your head around, because on an intuitive level, it looks like the integral should just have a value of 0, even if the top and bottom are divergent, they cancel out, but actually they don't. But as I say, guys, if you found that helpful, then leave a like, subscribe, and let me know in the comments what you thought of this. And if you have any other recommendations, then please hit me up with them and I will try to make videos on them. Thank you guys, as always, so much for watching, and I will see you in the next video. Cheers.